Case study of the day, Olivia. She was a healthy 35-year-old woman. Until one spring day when she got into a bad bike accident and suffered serious head trauma. The doctors patched her up, but after a couple of days in the hospital, she noticed something strange was happening. Or rather, something wasn't happening. She could no longer smell. Not the flowers in her room, not the nurse's rubber gloves, not even the horrible hospital food. In the weeks that followed, she blackened a batch of cookies because she couldn't smell them burning. She couldn't smell the lilacs blooming, or her husband's aftershave, or her car overheating. She drank expired milk because she couldn't taste that it had gone sour. The world got a lot less interesting. Eating wasn't very exciting, and Olivia started getting depressed. Life felt sterile and unfamiliar. Olivia had anosmia, a partial or complete loss of the sense of smell, and with it, most of her ability to taste. This unfortunate condition is caused by things as diverse as head trauma, respiratory infections, even plain old aging. And I say unfortunate because what we sense informs who we are. But how we experience our 6 major special senses all boils down to one thing: sensory cells translating chemical, electromagnetic, and mechanical stimuli into action potentials that our nervous system can make sense of. This process is called transduction, and each sense works in its own way. Our vision functions with the help of photoreceptors, cells that detect light waves, while our senses of touch, hearing, and balance use mechanoreceptors that detect sound waves and pressure on the skin and in the inner ear. But our sense of taste, or gustation, and smell, or olfaction, are chemical senses. They call on chemoreceptors in our taste buds and nasal passages to detect molecules in our food and the air around us. These chemical senses are our most primitive and our most fundamental. They're actually sharpest right at birth, and they're so innate that newborns orient themselves chiefly by scent. They can not only taste the difference between their mother's milk and another mom's, but they can even smell her breasts from clear across the room. Tastes and smells are powerful at activating memories, triggering emotions, and alerting us to danger. They also help us enjoy the small things that make life worth living, like pizza. Alright, I'm about to perform a superhuman feat and sit here with this amazing slice of Hawaiian pizza without eating it, so that I can describe it to you how we smell things. So if it sounds like I'm going fast during this episode, it's not that I don't enjoy our time together, I just want to get to the part where I actually get to eat the pizza. Now the process starts as I sniff molecules up into my nose. This means that for you to be able to smell something, the odorant must be volatile, or in a gaseous state to get sucked up into your nostrils. And yes, that means when you smell poop, there are actually poo particles up in your nose. The harder and deeper you sniff, the more molecules you vacuum up, and the more you can smell it. Most of these molecules are filtered out on the way up your nasal cavity as they get caught by your protective nose hairs, but a few make it all the way to the back of the nose and hit your olfactory epithelium. This is your olfactory system's main organ, a small yellowish patch of tissue on the roof of the nasal cavity. The olfactory epithelium contains millions of bowling pin-shaped olfactory sensory neurons surrounded by insulating columnar supporting cells. So these airborne pizza molecules, many of which are just broken off parts of fats and proteins, land on your olfactory epithelium and dissolve in the mucus that coats it. Once in the mucus, they're able to bind to receptors on your olfactory sensory neurons, which, assuming they hit their necessary threshold, fire action potentials up their long axons and through your ethmoid bone into the olfactory bulb in the brain, the resting membrane potential, and it sits at around -70 millivolts. Where do those charges come from? Outside of a resting neuron, there's a bunch of positive sodium ions floating around, just lingering outside the membrane. Inside, the neuron holds potassium ions that are positive as well, but they're mingled with bigger negatively charged proteins. And since there are more sodium ions outside than there are potassium ions inside, the cell's interior has an overall negative charge. When a neuron has a negative membrane potential like this, it is said to be polarized. But here's the wonder of specialization for you. Each olfactory neuron has receptors for just one kind of smell. And any given odorant, like this pizza, is made up of hundreds of different chemicals that you could smell, like the thymol of the oregano and the butyric acid of the cheese, and the acetylpyrazine of the crust. So after each smell-specific neuron is triggered, the signal travels down its axon where it converges with other cells in a structure called a glomerulus. This takes its name from the Latin word glomus, meaning ball of yarn, which is what it looks like. A tangle of fibers that serves as a kind of transfer station where the nose information turns into brain information. Inside the glomerulus, the olfactory axons meet up with the dendrites of another kind of nerve cell called a mitral cell, which relays the signal to the brain. So for each mitral cell, there are any number of olfactory axon synapsing with it, each representing and identifying a single volatile chemical. As a result, every combination of an olfactory neuron and a mitral cell is like a single note, and the smell coming off of this pizza triggers countless of those combinations, forming a delicious musical chord of smells. Now just imagine a piano with thousands of keys able to produce millions of unique chords, and you'll get an idea of how amazing our noses are. Scientists estimate that our 40 million different olfactory receptor neurons help us identify about 10,000 different smells, maybe even more. So once a mitral cell picks up its signal from an olfactory neuron, it sends it along the olfactory tract to the olfactory cortex of the brain. From there, the pizza smell hits the brain through two avenues. One brings the data to the frontal lobe where they can be consciously identified, like, oh, melted mozzarella, while the other pathway heads straight for your emotional ground control, the hypothalamus, amygdala, and other parts of the limbic system. This emotional pathway is fast, intense, and quick to trigger memories. If the odor is associated with danger, like the smell of smoke, it quickly activates your sympathetic system's fight-or-flight response. That's a big reason that Olivia's anosmia was so problematic. Without being able to smell, she couldn't access emotional memories wrapped up in particular scents or sniff out dangers in her environment. And these same intellectual and emotional dynamics apply to taste as well, because after all, taste is 80% smell. As you chew your food, air is forced up your nasal passages, so your olfactory receptor cells are registering information at the same time as your taste receptors are, so you're both smelling and tasting simultaneously. So it's true that if you have a bad cold or if you just hold your nose, your sense of taste is impaired, but it's not like you can't taste anything, it's just that more subtle flavors involve more volatile compounds that are picked up by your olfactory receptors. So you can hold your nose and taste that something is sweet, but you wouldn't be able to pinpoint it as being caramelized sugar. Likewise, you can taste that something is generally sour, but you can't tell the difference between a lemon and a lime. When I read this script, I didn't think it was going to be so difficult to do this, but it is very hard and I'm getting very hungry and I would like to get to the part where I get to eat the pizza. We are at the point, everyone, where I get to... So as soon as I take a bite, all the sensory information in there is quickly sorted by the 10,000 or so taste buds covering my tongue, mouth, and upper throat. Most taste buds are packed deep down between your fungiform papillae. Those little projections that make your tongue kind of rough, you can actually see them if you look in the mirror. Those papillae are not your taste buds. They're actually tucked into tiny pockets hidden behind the stratified squamous epithelial cells on your tongue. Each bud has 50 to 100 taste receptor epithelial cells, which register and respond to different molecules in your food. Notice that these are specialized epithelial cells, not nervous tissue, so they still have to synapse to sensory neurons that carry information about the type and amount of taste back to your brain. These epithelial receptor cells come in two major types: gustatory, or the kind that actually do the tasting, and basal, the stem cells that replace the gustatory cells after you burn them on a lava-hot, melty, cheesy Hot Pocket. Basal epithelial cells are extremely dynamic and replace the gustatory cells every week or so, which is why even a terribly burned tongue will feel better in a couple of days. Every gustatory cell projects a thread-like protrusion of the cellular membrane called a gustatory hair, which runs down to a taste pore, a small hole in the stratified squamous epithelium covering the taste bud and the rest of the tongue. In order to taste a bite of pizza, those food chemicals, or tastants, must dissolve in saliva so they can diffuse through those taste pores and bind to receptors on those gustatory cells, and then trigger an action potential. And each tastant is sensed differently. For example, salty things are full of positively charged sodium ions that cause sodium channels in the gustatory cells to open, which generate a graded potential and spark an action potential. Meanwhile, sour-tasting acidic foods are high in hydrogen ions and take a different route by activating proton channels. So taste, like all our senses, is all about how action potentials get triggered. Once an action potential is activated, that taste message is relayed through neurons via the 7th, 9th, and 10th cranial nerves to the taste area of the cerebral cortex, at which point your brain makes sense of it all and begins releasing digestive enzymes in your saliva and gastric juices in your stomach to help you break that food down so you can use it.